Hello again, everyone. We are in Chapter 10, and we're actually nearing the end of it. We are just barely getting into the last part, which is on elastic collisions. We've been talking about momentum and inelastic collisions, and we're going to do a few examples that get us into elastic collisions, which will finish out the chapter. So, this is example 10.9 right here, and before we get into it, we need to establish a few things about elastic collisions. Elastic collisions, the rules that govern elastic collisions are very much like the rules that govern inelastic collisions. For example, momentum, or the net momentum before the collision, equals the net momentum after the collision. Momentum is conserved. That's like saying m1 v1 equals m2 v2, or m final v final. Now usually mass doesn't change, rather velocities do change, but that's at least the principle for momentum. The momentum is conserved. But what is also conserved in elastic collisions is energy, kinetic energy. Kinetic energy before the collision, the sum of the whole system's kinetic energy before the collision is going to be equal to the sum of the kinetic energy after the collision, the final. We did a problem with two football players, and they ran at each other. Both of them together, their energy added up to quite a bit of kinetic energy, but then they stuck together, and then a lot of that energy dissipated. Here we have energy, kinetic energy, being absolutely conserved. And that's going to be the big difference in elastic collisions. So this example right here, I asked you to look at it last night. Well, many of you, I asked you to look at it last night. And I'd like you to be able to put this into your own words. We have what's called a Newton's cradle, and I think we've all seen these before. Here's where we have a series of ball bearings suspended on strings, and one is pulled back here, and it's let go. And the novelty of it is that momentum, not only is it transferred, and not only is kinetic energy conserved, but it's transferred through all these bearings right here, such that this one on the end pops out, and then it flies up and comes back down, and of course you've seen that happen before. Okay, so what rules this is absolutely what rules all other collisions. Number one, that is the conservation of momentum. So let's draw just a regular collision between two of these ball bearings right here. So we're going to have one right here and one right here. And this one is the one that we pull back and then let it go, and then it comes down and it smacks into another one right here, and that one flies up. Okay, so we have, right before this collision, right at this spot right here, we have a mass and a velocity, and afterwards, with this elastic collision, we have another mass, which is the same mass, times another velocity, which, well, it's not another velocity, it is the same velocity as before. You've seen these work. The same distance you pull it back is the same distance that this ball bearing flies up on the other side. So momentum is conserved. Not only that, but you've probably seen that if you pull two of these bearings back right here, okay, and then you let them go, and they swing down, and two of them collide with two other bearings, then these two fly out. So we're doubling the mass. So 2m1 v1 equals, after the collision, 2m2 v2. Okay? But what your friend says in this problem right here your friend says, looking at this balanced momentum equation, he or she says, okay, well, who says that this 2 right here has to go in front of the mass? Why can't you pull 2 masses out over here and then have there be 2 times the velocity on the other side? Because after all, if we did this, 2m1 v1 equals m2 times 2 v2, that's still a balanced equation, isn't it? That's still balanced. So he or she is saying, well, look, that's balanced, so how come you can't do this? How come you can't pull 2 masses out? Okay. Oh, come on now. And have them swing down. So that's 2m, 2 times the mass and velocity 1. Have them come swing down and hit a single mass right here and have that fly up with twice the velocity. So m2, 2 times velocity 2. That's what your friend is saying. He or she is saying. Well, if you've ever done this before, if you pull out 2 of these ball bearings right here, you always get 2 popping out the other side, like we have written above right here. But why does this idea, this concept, why does this not work for your friend? Why is your friend actually wrong? How is it that you can't double the mass and get a single mass with double the velocity over here? After all, this equation is balanced. Well, the answer goes back to kinetic energy. Not only do we have to worry about balancing momentum, but we also need to worry about balancing kinetic energy. In an elastic collision, the kinetic energy, the total system kinetic energy before the collision is equal to the total system kinetic energy after the collision. So that's like saying 1/2 m1v, or m initial v initial squared equals 1/2 m. Oh, did I just lock up here? Ooh, what was that? M final v final squared. Or I could say m2 v2 squared. So that has to be true. So what happens then if we take this equation, or these values for this equation, and stick it in for that right there? We would get this. We would get 1/2. In fact, I'll write it back up here. I'll write it down here. We would get 1/2 2 times m1. Okay, so we're starting out with twice the mass, times velocity 1 squared. I'm going to put a bracket around that and square it. That would have to be equal to 1/2 mass 2, which is really the same thing as mass 1, times 2 times velocity 2 squared. That's what we're saying. And the answer is you can't have that, because no longer is that equation balanced. Yeah, sure, the equation over here for momentum is balanced, but for kinetic energy, this is not true. Because look, we've doubled the velocity here, but that's squared. Here we've simply doubled the mass, and it's not squared. So the fact that you've got this square right here, that throws that whole equation out of balance. And so it is not true. It is not equal. It's because you must balance momentum, and you must balance, or you must conserve, kinetic energy. There you go. It's example 10.9, and we're going to be dealing with more balancing of momentum and kinetic energy in future problems. So I'll see you in the next video.